Hi, everybody. This is the weirdest thing I've ever done. I'm in a hotel room in Casper making your lesson for tomorrow. I did a lot during COVID with Zoom and videos, but it's been a while. And you'll never guess what. It is windy in Casper right now. I know, can't believe it. Anyway, I'm gonna do your quick video lesson on graphing logs. And I just have your plan of attack pulled up right now because I will also post a link to our notes as soon as I get done writing on them right now. Then I want you to work on that worksheet 6.4. Press pause on the video right now if you need to switch and get to this page of notes on logarithms. And now I want you to fill out as much as you can of this table about a mystery function. You're going to try to figure out the relationship between x and y. And fill out again as much as you can and try to start answering number 1 or number 2. And then we're going to graph it together on number 3. Press pause on the video while you fill out the table. Okay, so now did you get some of these values? There were a few that didn't work, but hopefully you started noticing, especially I like these two right here, where you might have noticed 2 to the 4th is 16 and 2 to the 3rd is 8. So it's that y is the exponent and x is the output. So the rule that you might have written on number 1 could look like 2 to the y equals x. And of course, on my table, you see there are some outputs you wouldn't have been able to find values for. We cannot solve 2 to the question mark equals 0 because there's nothing that works there. And 2 to the what makes -1 does not also work. And the other hard one that you can't do without a calculator is 2 to the what makes 3. It's got to be a decimal number. And this is where logs, again, would come in handy. You could rewrite it as a log expression and then use your calculator to get an answer right away without all that guessing and checking. So on number 3, where it says graph the ordered pairs that we did in the table, this is going to be the log graph that we're graphing. So getting a few of these ordered pairs placed correctly would look like 1, 0, 2, 1, 8, 3 are some of these whole numbers. And 4 to the right, 2 up. This is enough on the upper side. And then getting a few of the fractional x values, when you go right a half, it's down 1. And when you go right a fourth, which we didn't have in our table, but we had right 1/8, which is really hard to graph, you'd be down 3. So again, you have this smooth curve that does keep increasing in the y values forever. And then it drops off to the -infinity in the y values as x gets closer to 0. Give the domain and range of the function would be that the domain has to be from 0 to infinity. Use parentheses because we're not including 0. And the range is -infinity to +infinity. Or you could just put all real numbers. Find and graph the inverse of the function. So now that's just, let's swap a few of our ordered pairs. And so we want to go 0, 1 instead. Instead of 2, 1, we want to go 1, 2. Instead of 4 to the right, 2 up, we want to go 2 to the right and 4 up, and so on. And you can see that this half will look like an exponential curve. When we go left 1, where's that one? You go up a half or left 1. And then it just keeps getting smaller and smaller. Flatten it out against the x-axis. That is an exponential. function, whereas the original one we graphed is a log function with base 2. So to find the inverse, when it says find and graph, when we find it, that's just swapping x and y. So on that original function right here, we want to just write 2 to the x equals y. And that is in the right form already because we want y isolated in any function. So when we go to graph a new log graph and we don't know what it looks like, we can use its inverse to help us graph, which is not the way I did the top one. So this time I want you to think of the inverse first, which is 5 to the what equals what? And so 5 to the y, basically we should call it, which is like having h of x over here. 5 to the y equals x, but when you swap x and y, you get the inverse. 5 to the x equals y. If you didn't still know what that exponential looks like, we could plug in a few values for x. Of course, anything to the 0 is going to be 1. So right now I'm graphing the exponential. 5 to the first is going to be 5. So now you can start to see that as you move right one with x, it's getting 5 times bigger. We don't even have room to graph the next one, which would be 25. So if we get one in the backwards direction, if I plug in a -1 for x, the y value would be 1/5. That is going to be enough points. Sometimes 3 points on an exponential is all you can graph. But that's not the right answer to number 6. If it said graph the log function, we have graphed its exponential function. So when we graph its inverse, it will be the log function. So we want to do 1, 0. And when you go right 1/5, you are down 1. And when you go right 5, you are up 1. When you get done graphing these, they should look pleasing to the eye and symmetrical across that line y equals x. So this one is log base 5 of x. And I could put h of x in front of that or y equals in front of that. I'm sure part of the weird thing right now is when do you know to swap x and y and when not to? But a log becomes an exponential when you swap x and y, you get its inverse. Okay, on number 7, this means for any log graph with any base, as long as it's a number above 0 and not 1, the domain will always be from 0 to infinity. And this is assuming there's no shifting left, right, up, down, any of that stuff. This is our most basic log graphs. The range will be all real numbers or -infinity to infinity. The x-intercept will be 1, 0. There won't be a y-intercept. And the asymptote will be the y-axis or x equals 0. A vertical line that it's getting closer and closer to, but will never cross. Press pause on the video if you need to catch up. All right, on the back side of these notes, I already filled in a little bit. To graph an inverse, you could first switch the input and the output, make sure it looks symmetrical across the line y equals x. You can see that on the previous example, I wrote it as an exponential and then swapped x and y though. The thing to notice here about an exponential growth graph, its log graph, has this shape of the red one. And then this is really funny. An exponential decay graph will actually intersect with its log inverse graph. Okay, this little section should be reviewed. Just a reminder of what do logs do? They help you think of the exponent that would be on the base that gives you the value. So 2 to the 5th gives you 32. 5 to the 1st gives you 5. 49 to the second gives you 7. If we're just evaluating those expressions, it's not really like we're solving an equation, so I don't put x. The next row, we have to remember that the common log, when you don't see a subscript, means that it is log base 10. So 10 to the what, making a 1 over 100 has to be a negative exponent, and 10 squared is 100, so it has to be a negative 2. And I apologize the other day for making a small mistake on our notes, but I need to clarify it now that when you see natural log, it is equivalent to log base E. And if you don't believe me, you can type these in separately to your calculator and see that they give you the same exact value. So what I'd like to do on this one is transform it into log base E, e to the third, and then remembering that any base with its other number there cancels out, and so the value would just be 3 here. And then again, on the last one, log base 2 of 2 cancels out. But if you want to think of 2 to the what gives you 2, it can only be a 1. Okay, one more log graph before you start working on the 6 questions on your worksheet 6.4. If you had to graph log base 3, you want to write the inverse, which first write its exponential. So first I'm going to go up here and go 3 to the y equals x, which then swapping x and y would be 3 to the x equals y. And of course, that looks better if we write y equals 3 to the x. So it feels more like an exponential function. So we're going to graph that one. The most basic log graphs always go through 0, 1 because it's as if I could rewrite it with a 1 as the initial value in front of that 3 as our base to the x. And if you aren't sure still where to graph these things and understand that tripling rate, just make a table of values. But this does go through 0, 1, and then just double checking if I plug in a 1, I have to go 3 to the first, which is 3 times 1, which is still 3. So write 1 up 3. And then it triples again. So the next one would be 9, but I can't really fit that on my graph, so I'm going to not put it. When I go back 1, I would be at a 1/3. And then even back 1 more would be a 1/9, which you're running out of the ability to graph that. So just flatten it out against the x-axis. This one is the exponential graph. We still don't have the ultimate goal, which is the log graph, but now just flip-flop any of those x, y ordered pairs. So we need 1, 0. And then when we go right 3, we need to go up 1. When we go right 1/3, we need to go down 1, and then make your nice smooth curve. Both directions, and don't cross that y-axis. This would be log base 3 of x, or y equals log base 3 of x, or g of x if I used the function notation. One last little thing I guess I could put next to this is this would be g inverse up here, this purple one we graphed, which is the exponential. Last, I thought this would be a fun one on your graphing calculator. It's about the length and width or weight of alligators in inches and in pounds. They've written a natural log graph to represent that. And if you type this in your y equals screen, make sure everything else is cleared out first. Type it in exactly like you see it. You will get a curve that looks like a log graph. If you can't see it when you first initially type it in and graph it, try to hit zoom fit, which is, I believe, zoom 9 or zoom 0. You can always scroll through and double check, or zoom out, but then you have to press enter to make it zoom out. If that doesn't work, you could always open the Desmos graphing calculator because that is a lot friendlier to zoom in and out.